At 14:02 UTC, while half the world was settling into afternoon routines and the other half was waking up, an unexpected ripple went through the global astronomy network. It was subtle at first, almost invisible, just a few odd telemetry pings, a dropped packet here, a calibration loop restarting itself there. Nothing that would suggest that something unprecedented was unfolding 93 million miles away near the blazing curve of the sun. But then the ripple grew, it sharpened, it synchronized, and within seconds, every major skywatching instrument on Earth reacted as if they'd all witnessed the same impossible thing at precisely the same instant. This wasn't a solar flare. There were no warnings from the space weather monitors. The sun's surface was calm, almost eerily so. Yet the instruments behaved as though they had been struck by a sudden burst of radiation. Consoles froze mid-frame. A dozen real-time spectral analyzers at observatories across Europe and East Asia jumped to maximum brightness before going dark. Streams of otherwise stable numbers, temperature baselines, polarization metrics, coma shape indices became ragged, nonsensical spikes before collapsing into static. In Chile, at the Atacama facilities, several researchers would later describe the exact second the anomaly hit as a whiteout, not visual, but data whiteout. Panels that had always displayed smooth spectral curves erupted into jagged mountains of noise. One researcher instinctively slapped the emergency lockout on his terminal, convinced the system had overheated. When he checked the hardware temperature, it was perfectly normal. On the other side of the planet, in South Korea, technicians monitoring solar interferometers saw the fringes, the delicate ripple patterns used to track precise distortions, twist as though something refractive had flickered across the field. For several long seconds, none of their internal models could interpret what the sensors were seeing. A junior researcher shouted for verification, thinking it was a software error. By the time a senior scientist reached her station, the pattern had stabilized again, leaving only corrupted logs and several blinking error codes behind. The timing of all of this was too precise to ignore. It aligned almost perfectly with the moment 3I Atlas reached its closest point to the sun. No one knew this immediately. The shock had hit too fast, leaving every team to assume their own equipment had failed. But within minutes, as observatory after observatory posted urgent requests for cross-checks on internal channels, it became clear that this wasn't an isolated malfunction. It was everywhere. The crisis spread next to the solar monitoring satellites. Stereo A, which had been tracking Atlas through its coronagraph instruments, dropped half a frame before its automatic protection protocols kicked in, temporarily suspending its imaging suite. The GOES-19 coronagraph reported what its internal system labelled an over-luminosity event, a term most operators had never even seen because it was meant only for theoretical test cases. Even the usually unshakable Solar Dynamics Observatory experienced a brief but measurable dip in telemetry bandwidth, something that had only happened during solar storms or spacecraft anomalies. But there was no storm, and the spacecraft was fine. What wasn't fine was the point in space where Atlas should have been. The first partially recoverable frame from Stereo A arrived almost 5 minutes later. It looked broken, smeared, useless at first glance. But buried in the distortion was a shape, a faint, stretched silhouette, elongated, brightened, and displaced slightly off the predicted trajectory. That tiny shift was enough to make the mission lead at Johns Hopkins lean in toward her monitor and mutter one stunned sentence that a team would replay over and over. "That's not where we left it." The displacement didn't make physical sense. Whatever force had acted on Atlas hadn't pushed it away from the sun or closer to it or along any predictable curve. It had nudged it sideways across its expected orbital path. A natural jet could do that, maybe, but not in the clean, instantaneous way the instruments were suggesting. A jet leaves a plume leaves particulate scatter. Scatter leaves dust signatures. And dust signatures light up coronagraphs like powdered glass in sunlight. There was nothing, only light, brightness, saturation. At NASA's Goddard Center, a small team reviewing the ultraviolet logs from ESA's Vigil mission discovered that Atlas's UV reflectivity hadn't merely increased, it had warped. For 5 frames, the object radiated in a pattern that didn't match coma behavior, gas release, or thermal shock. It looked instead like a sheath of energy blooming around the nucleus, expanding too fast to be physical material and collapsing too smoothly to be a chaotic outburst. It was a flare without ejector, a burst without debris, a breath of light. The theorists immediately reached for comets, as we know them, explanations, runaway sublimation, structural collapse, exposure of fresher ice layers. But the numbers coming in from Europe and Japan didn't match any of those models. The flare rose too rapidly, then decayed too cleanly. It behaved more like a triggered event than a natural reaction to heat. Meanwhile, mission coordinators across multiple time zones exchanged frantic messages trying to establish whether the disturbance had originated from Atlas or from the Sun. But the Sun's own telemetry was boringly normal. Baseline magnetic readings held steady. Solar wind didn't spike. Nothing from the star itself justified the global data disruption. The conclusion was impossible to avoid, yet no one wanted to be the first to say it out loud. Whatever hit the instruments came from Atlas. And no one had any idea how, by evening, private Slack channels at major institutions were filled with clipped conversations. Someone asked whether Atlas might be fragmenting. Someone else pointed out that fragmentation would have been visible in coronagraph filters. Another suggested that they wait for James Webb's infrared refresh. Another simply typed, "We need to see inside it." The fear wasn't that Atlas had changed. The fear was that it had changed in a way no known physics could account for. As late-night meetings began in Houston, Madrid, Tokyo, Seoul, and Canberra, the same troubling question surfaced across every discussion, spoken cautiously at first, then with building urgency. Why did every major instrument on Earth momentarily break at the exact second 3I Atlas reached perihelion? It wasn't the brightness alone. It wasn't a solar event. It wasn't interference. It wasn't a coincidence. Something had happened inside that object, something powerful enough, sudden enough, and strange enough to ripple through the entire observational network of an entire planet. And this was only the beginning. In the hours after the perihelion shock, the world's observatories scrambled to reconstruct what they had missed during the blackout. Teams downloaded corrupted frames, patched together half-complete data, and adjusted instrument sensitivity ranges to avoid another saturation cascade. But no one expected what would emerge once the first clean images finally came in. 3I Atlas was not shaped the way it had been before perihelion. Hours earlier, it had been a faint, irregular, but recognizable interstellar comet, compact, smooth along its silhouette, stable in its spin rate. The nucleus geometry had been one of the few things observers actually felt confident about. But after perihelion, the object wasn't simply brighter. It was different, longer, narrower, twisted in a way that should not have been possible in so short a time frame. It was as if the object had been pulled, stretched, and compressed all at once. When Stereo A's first stabilized post-event frame arrived, the mission analysts didn't know what they were looking at. The nucleus no longer resembled a lumpy sphere, but a tapered spindle, elongated by what appeared to be dozens of meters along its major axis. That alone would have been bizarre. But the next frame, captured 37 seconds later, showed a different shape. The spindle had compressed, becoming shorter but thicker, as if the object was flexing. Comets do not flex. Across the Pacific, Japan's solar monitoring arrays confirmed the deformation. Using high-frequency imaging taken near the solar limb, researchers saw Atlas's brightness contour oscillate. It seemed to pulse slightly, like a jelly stretched between invisible forces. One researcher compared the deformation to a heartbeat. Another corrected him. Heartbeats are periodic. This was not. The changes were irregular, unpredictable, almost frantic. The initial assumption was fragmentation. Maybe the nucleus had cracked and pieces were tumbling, giving the illusion of shape-shifting. But that theory collapsed immediately when spectrographic logs showed no debris cloud, no dust plume, no dispersal signature of any kind. The silhouette was changing, but the mass distribution wasn't producing the scatter expected from a breakup. Whatever Atlas was doing, it wasn't falling apart. It was changing form. Theories poured in. Some were cautious, grounded in physics. Others, whispered quietly in late-night conference calls, were less comfortable. The most conservative possibility was non-gravitational torque, essentially. Atlas's outgassing jets pushing the nucleus into wild rotational states. Comets experience this all the time, but only in predictable ways. A jet firing from a crack in the surface can accelerate or slow spin, cause a wobble, maybe shift the orientation a few degrees. But this was nothing like a wobble. This was rotational chaos. Stereo A's light curve showed that Atlas's spin rate was not just speeding up or slowing down, it was oscillating. Sometimes the object rotated rapidly, completing a turn in minutes. At other times, the rotation nearly halted. These were not mechanical changes caused by torque. They were spasms. Cryovolcanic jets, perhaps? Jets bursting from deep inside the object, firing in different directions as volatile pockets were exposed. This worked on paper, except cryovolcanic jets produce distinct thermal signatures. They heat the region around the jet, altering infrared readings. But Webb's infrared instruments, now fully reorienting after perihelion, found no such hotspots. Atlas was cold, too cold for jets that powerful. The second theory was more exotic, a form of fracturing unseen in any other object. Not a breakup, but an interior collapse causing temporary reshaping. If the nucleus was honeycombed with cavities, spaces carved by ancient radiation or formed during its birth around another star, then the stress of perihelion might trigger sudden shifts. But these shifts would be localized, irregular, asymmetric. They wouldn't produce the smooth, continuous reshaping Atlas displayed. The third theory was something no one wanted to write down officially. A well-known comet physicist in Italy summarized it quietly during a late-night exchange. It's behaving as if it's elastic. Elastic was not a word that belonged anywhere near comet science. Elasticity implies structure, framework, material cohesion. Interstellar objects, especially icy ones, are brittle. They fracture, they crumble, they shed dust, they do not stretch. But Atlas appeared to be doing exactly that. By the next morning, the full extent of the anomaly became impossible to downplay. Observatories analyzing the object's light curve noticed periodic dips and surges that correlated with its deformations. As the object elongated, it brightened in the ultraviolet. As it compressed, the UV dipped and the visible spectrum intensified. Something was happening internally, something driving the object to alternate between shapes, as if energy was moving through its core in waves. Hours after sunrise in Europe, a remarkable sequence arrived from ESA's Vigil mission. 12 consecutive frames showing Atlas twisting. not rotating, twisting. As if one end of the nucleus rotated faster than the other, causing torque along its length. If true, that meant the nucleus wasn't a rigid body at all. It was deformable, possibly layered, possibly something far stranger. This sparked a new hypothesis: differential density. If Atlas contained regions of material with dramatically different strengths or melting points formed around a star whose chemistry bore no resemblance to our own, then the perihelion heat might activate these regions in unpredictable ways. But this raised another question. Why did the deformation happen instantly at perihelion, not gradually as temperatures increased? A few daring researchers proposed an almost unthinkable possibility: that Atlas's internal structure was not stable, not fixed, not even bound in the way comet nuclei usually are. Instead, the object might contain long chains of carbon or silicate material capable of flexing before fracturing, something akin to frozen minerals under tension, but with structural memory, material that bends before it breaks. And still, the shape changes continued. The more images came in, the clearer the pattern became. Atlas was cycling between forms, elongated, contracted, twisted, expanded, over and over again, never settling, never returning to the shape it had before. The sequence looked almost like breathing, not literal, of course, but dynamic, alive with motion, responsive. There was no way to describe this object using the language of comets anymore. It wasn't a comet by behavior, by rotation, by structure, or by anything the scientific community understood. If it was a relic of another star system, then it carried physics from that system as well, physics we had never encountered. One line from a British researcher's internal briefing circulated across several institutions. He didn't mean it to become a mantra, but it did. This is the first interstellar object whose geometry is actively changing. And with every new frame, that statement became harder to dispute, because Atlas was no longer a visitor passing through our solar system. It was a phenomenon rewriting itself in real time, shifting, twisting, reshaping, leaving humanity to wonder not what it was made of, but what it was becoming. No one expected the colour blue to become the centre of the mystery. It wasn't on anyone's checklist, not in any early predictions, not in the briefings circulated through the planetary science Slack channels. Comets glow green, or sometimes red, or faintly cyan when excited by the solar wind, but a vivid, structured, near-ultraviolet fluorescence was not supposed to be part of 3I Atlas's story. And yet, in the hours after perihelion, while Earth's ground-based observatories were wrestling with their overloaded sensors and unexpected dead zones, there was one instrument in the entire solar system still functioning with perfect. ESA's Vigil solar mission, parked at L5, quietly collecting its spectral survey of everything in the sun's vicinity. When Vigil's automated filters flagged an emission line no one had ever seen, its onboard system didn't sound an alarm. It simply logged a note, assigned it a standard anomaly code, and transmitted the data packet. Only when the raw stream reached mission control hours later did a human set eyes on something that would force the entire room to fall silent, a razor-thin fluorescent band in the near UV, narrow and bright, with an energy distribution that did not match any known molecular emission. It wasn't random noise, and it wasn't contamination. It had structure. It had symmetry. Most striking of all, it pulsed, not fast, not like a beacon, more like a breath, a rise and fade every 90 seconds, steady as a metronome. Within minutes, teams began pulling up comparisons. Nothing from our own comets fit. Nothing from Oumuamua's spectroscopic archive matched. Nothing in the catalogue of exotic photochemical reactions predicted anything close to this behaviour. It was too clean, too periodic, too coherent. And the signal wasn't distributed across its coma like natural fluorescence. It was constrained to a tight region near the nucleus, almost like a sheath. The first instinct was to blame Vigil's detectors, space weather interference, solar wind injection, cosmic ray artifacts, anything that could mimic a band like that. But the timing was wrong. Vigil had just come through one of the quietest solar wind windows in recent months. Its sensors had registered no sharp particle events, no gain shifts, no internal heating spikes. The anomaly was external, and it was real. Theories began forming almost immediately. Some pointed to exotic interstellar ices, complex organic molecules formed under different cosmic ray environments. Others suggested pressure-induced electronic transitions that occur only under the kinds of internal stresses 3I Atlas had displayed during its shape-shifting episodes. A few proposed that the UV excitation was a byproduct of sublimation from materials that never form in our solar system, ices that would collapse into unrecognizable fragments long before they reached the inner system if they originated from here. But before anyone could fully digest the ultraviolet puzzle, a second anomaly emerged. This one came from the opposite end of the spectrum, and it made even less sense. Infrared telescopes on Earth and in orbit had finally stabilized after the perihelion sensor crashes. When they began gathering post-event data, a pattern emerged that should have been impossible. 3I Atlas was too cold, or, more precisely, it wasn't radiating the heat it should have after its violent close pass around the Sun. Every object that approaches perihelion absorbs immense solar energy and re-emits it as infrared heat. It's basic thermodynamics. Even Oumuamua, with its strange acceleration and non-reflective surface, obeyed that rule. But the infrared spectrum coming off 3I Atlas had a hole in it, a literal void, where thermal radiation should have been saturating the sensors. There was a faint tail of heat, yes, but it was anomalously weak, orders of magnitude lower than expected. Some researchers initially suspected calibration errors induced by the earlier telemetry failures, but after cross-comparing data from instruments that didn't share hardware, software, or even orbital locations, the conclusion became unavoidable. The object was cooling too efficiently, shedding heat in a way no natural material should. The void lined up disturbingly with the same region where Vigil detected the UV fluorescence. Something was happening inside or near the nucleus, something that absorbed heat, re-emitted it at the wrong wavelengths, or redistributed it internally before releasing it in ways we don't understand. One physicist described it as a photosynthetic process in reverse, metaphorically. But the quote spread through science social media faster than she intended. Another suggested a form of non-thermal electronic excitation, a mechanism where energy is shunted into metastable states instead of re-radiated as heat. But there was one hypothesis no one wanted to voice publicly, even though it circulated in private channels almost immediately, that the object wasn't cooling, it simply wasn't absorbing heat in the first place. Some material, some structure, some property of its surface or interior might be interacting with sunlight in ways that prevent normal thermalization. Maybe it was refracting solar energy internally, or redirecting it, or converting it through a cascade mechanism that ends in ultraviolet fluorescence instead of warmth. The notion was radical, but it fit the data better than anything else. A cometary physicist in Japan suggested that the nucleus might be covered in a quasi-crystalline matrix, something like a photonic lattice that channels incident light into specific resonance modes. No one knew how such a structure would form naturally in interstellar space, but no one could rule it out either. Interstellar molecular clouds host pressures, temperatures, and cosmic ray fluxes that have no analogue in the solar system. Materials can form there that defy simple intuition. By the second day after perihelion, 4 live telecons were running simultaneously across 3 continents. Every one of them kept circling back to the same uneasy pairing. Too much ultraviolet, not enough infrared. Too much order in one region of the spectrum, and too much emptiness in another. The symmetry of it bothered people, the coherence. Natural processes are messy, chaotic, noisy, but the band Vigil detected was crisp and periodic. The infrared void was wide, smooth, almost sculpted. Some suggested the 2 anomalies were linked through a single mechanism. Others argued they had to be independent because the energy budgets didn't match. A few countered that we might be dealing with a process that simply doesn't exist on any natural object in the solar system. It wasn't a satisfying conclusion, but it was the only one that didn't contradict data. The public didn't know any of this yet. Press releases were still being drafted, language was being softened, edited, stripped of implications. Words like unprecedented and novel process were kept. Phrases like coherent emission, thermal deficit, and energy misalignment were cut. But inside the research teams, no one was pretending this was normal. The debate spilled past midnight, then past dawn. Spectral models were pushed until laptops overheated. Some researchers proposed that maybe the fluorescence was caused by dust grains acting as tiny optical cavities. Others countered that the pulsing periodicity made that impossible. The idea of a rotating beam was raised, then dismissed. The possibility of resonance pumping through solar flux lines was sketched out, built, torn apart within an hour. And through all of this, 3I Atlas moved farther away from the sun, dimming slightly, not cooling, not behaving like anything bound by the familiar rules of heat and light. Every hour brought a new data point, and every data point deepened the contradiction. In the end, one phrase quietly emerged among the senior analysts, never spoken publicly, but repeated in private messages, late-night emails, and whispered discussions during telecom breaks. This object is radiating too much blue light and not enough heat. No one knew what that meant yet. But they all knew it was the beginning of a different kind of story, one where the laws of physics still held, but the universe had found a way to express them through matter we had never encountered before. This wasn't a comet. It wasn't an asteroid. It wasn't anything we had prepared for. And it was still changing. For the first time in days, 3I Atlas looked quiet. Not serene, never that, but strangely subdued, as if whatever had torn through its structure at perihelion had finally run out of momentum. The violent jets that erupted in the hours around closest approach, the geometry warping torque cycles, the ultraviolet pulses, they all softened into a pattern so smooth it felt artificial. When the first stabilized post-perihelion images arrived from the Chilean arrays, the global reaction wasn't relief, it was suspicion. Objects that undergo massive energy release don't simply settle into perfect symmetry. They recover, yes, but chaotically. They spit out dust, wobble, precess, fling off new vents. If the perihelion event really had fractured the interior, if the nucleus had been flexing, elongating, folding on itself, then every model predicted turbulence for days. Instead, spectral telemetry and visual data showed the cometary coma flattening into an almost laminar flow with no major outbursts, no temperature spikes, no strange pressure signatures. For something that had just been unraveling, this wasn't a cool-down phase. It was a silence. The first hints came from the thermal analysis teams reviewing infrared light curves. Even though the infrared void persisted, an absence of heat that made no physical sense, the small amount of thermal emission that was detectable stabilized abruptly. It locked into a flat line that didn't track its distance from the sun, didn't respond to sublimation fluctuations, didn't seem to acknowledge that it was losing mass at all. It was as though the object had found a new equilibrium one that didn't belong to any known cometary physics. At the same time, the coma's expansion rate slowed. Not just slowed, equalized. It formed a shell-like boundary with a consistent thickness, as though it wasn't diffusing naturally, but being regulated, controlled by something deeper in the nucleus. For researchers accustomed to dealing with comets, some of the most unpredictable bodies in the solar system, this behavior read like an insult to intuition. Comets don't regulate anything. They fall apart. They hiss. They shed. But 3I Atlas had entered a state that looked more like recovery than decay. Some analysts argued this was an observational illusion, a lull created purely by geometry. The object had rotated in a way that hid its most volatile fractures from our view. Others suggested that the perihelion blasts had expelled the last accessible volatiles, leaving nothing active to drive further outflows. But that hypothesis collided immediately with the continued UV fluorescence detected by ESA's Vigil mission. Something was still happening internally, something energetic, something structured. By the second day after perihelion, the calm became the subject of internal debate threads with titles like "This is not stability" and "We're missing something big." Instruments had recovered enough for deeper investigation, and a wave of new data, not dramatic, but precise, started to challenge the idea that 3I Atlas had quieted at all. The first breakthrough came from the dust polarization teams. When they reanalyzed light scatter patterns from just before and just after the lull began, they found something no one expected. The orientation of the dust grains had changed in a way that implied a sharp drop in internal pressure, not a gradual release. A sudden equalization. The object hadn't calmed down, it had depressurized. This was where one of the more intriguing theories emerged, what researchers started calling self-shadowing fractures. In typical comets, fractures exposed to sunlight heat up and vent more vigorously. They widen, branch, and destabilize the nucleus. But if fractures propagate inward in a certain configuration, they can begin blocking their own heat exposure. A fracture can cast a shadow deeper than its own geometry would suggest. In 3I Atlas's case, if the internal structure was already complex, full of cavities, flexures, or something more exotic, the fracture network might have temporarily shielded its most volatile subsurface layers, isolating them from the heat that should have torn the object apart. This theory didn't completely fit, but it explained the timing. The perihelion event may have ripped open a series of cavities all at once, equalizing internal gas pressures in a rapid, explosive cycle. After that, instead of more outbursts, the system quieted, not because it was stable, but because the internal forces had momentarily balanced. Imagine a sealed chamber with dozens of connected rooms, break enough doors at once, and suddenly everything inside becomes the same pressure. No more gradients, no more pockets waiting to rupture, just a temporary, unnatural stillness. And yet, this explanation only addressed part of the puzzle. It didn't explain why the object's thermal emissions plateaued so precisely. It didn't explain why the UV band pulsed with metronomic calm. It didn't explain why the coma wasn't expanding chaotically. And it didn't explain the data anomaly that arrived next, which shattered whatever lingering comfort the equalization hypothesis provided. The rotation analysis. Before perihelion, 3I Atlas had been a wild problem for angular momentum tracking. Its axis drifted unpredictably. Its shapeshifts made moment of inertia calculations impossible. But right after the explosion, and exactly when the lull began, its rotation stabilized. Not slowed, not accelerated, stabilized, as though the internal mass distribution had reorganized into something symmetrical. Not spherical, not rigid, but balanced. Several labs independently discovered this within hours, and their reactions were similar, a kind of stunned, reluctant respect. This wasn't the behavior of a dying object, it was the behavior of a system that had completed some kind of transition. A few researchers began using a word informally, cautiously, in private notes. Reset, not repair, not recovery. A return to a baseline state, one that didn't match the object's behavior before perihelion, but looked strangely optimized for its new trajectory outward. The lull, then, was not the aftermath of chaos. It was the establishment of order. A handful of analysts argued that this might be a natural process. Interstellar comets are subject to stresses we can't model easily. Perhaps 3 I-Atlas contained layers of material that only became active under direct solar heating, and then inert again once the energy dissipated. Maybe its structure was so porous that the internal collapse created a temporary symmetry. Maybe the UV fluorescence and infrared void were the results of some unique crystalline or amorphous state forming after the pressure equalization. The optimists clung to those ideas. Everyone else noticed the same pattern. Every major anomaly, from the spectral behavior to the shape shifting to the mass loss plateau, was converging toward a similar unsettling conclusion. This object was not acting like something falling apart. It was acting like something reorganizing. As 3 I-Atlas drifted farther from the sun, the lull persisted. The pulses in the UV band held their rhythm. The thermal deficit stayed flat. The nucleus maintained its newfound rotational consistency. Its coma retained its shell-like, regulated boundary. Nothing about it suggested exhaustion. Everything about it suggested deliberation, if not in intent, then in mechanism. The calm was not calm at all. It was a system resetting itself after a transformative event. And in the days ahead, the world would begin to understand what that reset had prepared it for. The lull should have been the end of the story, or at least a soft pause in it. After all the fracturing, the pressure equalization, the impossible stabilization of rotation, astronomers expected 3 I-Atlas to fade into a predictable outbound coma. Ice sublimates, gases disperse, the coma shrinks, the nucleus cools. That's the script. But instead of diminishing, the calm set the stage for something no one was ready to see. 3 days after perihelion, ESA's Vigil mission uploaded a new batch of coronagraph images. These weren't the compressed, near-real time frames the public sees. These were the high-resolution composites reserved for internal analysis, full spectral overlays, enhanced contrast, polarization channels. Technicians reviewing the data noticed something odd before they even understood what it was. A narrow streak of material, sharply defined, carved out of the surrounding halo. A collimated line. It didn't diffuse. It didn't bend. It simply extended from the nucleus like a needle. Then they noticed a second one, opposite direction. Same sharpness, same luminosity, same angle. The initial reaction was confusion. The next reaction, the one that rippled silently across Slack threads, analyst groups, and late-night video calls, was disbelief. Comets produce jets. Violent, chaotic jets. Hundreds or thousands at random, orientations, depending on rotation, surface morphology, and thermal gradients. But they do not produce twin, opposing, collimated jets like these. Not symmetrical, not narrow, not stable, and certainly not in perfect alignment with each other. The Vigil team triple-checked the contrast filters. They scanned for compression artifacts, for sensor ghosts, for cosmic ray streaks. Nothing. The jets were real. They emerged from opposite regions of the nucleus at nearly exact 180-degree separation, forming something that looked disturbingly like thrust vectors. But before that interpretation took hold, the scientific community reached for every natural explanation they could muster. The first hypothesis was a paired fracture system, two vents aligned along the nucleus's longest axis, activated after perihelion when trapped volatiles finally escaped. If the nucleus had cracked cleanly in two major directions, the jets might, in theory, appear opposite each other. But this explanation died quickly. The jets weren't just opposite, they were precise to within a fraction of a degree. Natural systems don't honour geometry that tightly, especially not in bodies that had just undergone extreme structural deformation. The second hypothesis involved cryovolcanism, a phenomenon occasionally suspected in distant icy objects like centaurs or Kuiper belt bodies. If 3I Atlas had internal reservoirs under uniform pressure, perhaps its internal reset had forced two vents to open simultaneously. Yet cryovolcanic plumes do not produce narrow streams. They billow, they fan, they spread. These jets didn't spread at all. A third camp proposed magnetic alignment. Maybe 3I Atlas contained ferromagnetic or diamagnetic materials oriented along a long-buried internal core, guiding jets along inherited field lines. But that idea collapsed as soon as rotation data came into play, because this was the detail that changed everything. The nucleus of 3I Atlas, while more stable than before, was still rotating. Not wildly, not erratically, but undeniably spinning in a slow, measurable, wobbling procession. The rotation axis tilted several degrees per hour. This movement should have dragged the jet directions with it. Comet jets don't stay pointed at a fixed angle, they sweep arcs as the body turns. But these jets didn't move. They ignored the rotation. They stayed locked in the same orientation, perfectly opposed, while the nucleus turned beneath them. This was the moment when the slack threads went quiet. When people who usually typed paragraphs in seconds paused for minutes. When the double checks turned into triple checks, then into calls across agencies, across countries. If the jets were anchored to surface features, they would rotate. If they were driven by internal fractures, their orientation would shift. If they were shaped by pressure vents, they would drift as gas escape fluctuated. But they didn't do any of that. The jets acted as though they originated from a fixed reference frame outside the rotation of the nucleus. Only one natural explanation remained. Perhaps the jets weren't anchored to the surface at all. Maybe they were being shaped by something further out, like the coma's electromagnetic environment or solar wind interactions forming stable channels. Yet, modelling that idea immediately hit a wall. The solar wind is not a stable sculptor. Its turbulence alone would have shredded such symmetry. And that's when the most unsettling implication began circulating, not loudly, not officially, but quietly, cautiously. The jets behave like controlled exhaust, not purposeful, not technological, just controlled, in the sense that something about the system maintained geometric consistency independent of rotation. Something about the object was regulating the outflow. Some compared it to spontaneous plasma collimation in astrophysical jets, those vast beams of matter emitted from black hole accretion disks. But that was a metaphor at best. Black hole jets emerge from enormous magnetic structures. 3I Atlas was a 1-2 kilometers object at most, with no detectable magnetic field strong enough to produce anything like that. Another group suggested the jets were a balancing mechanism. The object had been destabilizing before perihelion. The reset may have reorganized internal materials so that any gas pressure released afterward escaped only through two optimal points, inward fractures meeting at structural weaknesses that naturally aligned. But again, nothing explained how the jets resisted rotational drift. The more conventional explanations remained on the table in theory, but every hour of new telemetry made them harder to defend. Because in each dataset, spectral, polarization, thermal, UV, the jets didn't just remain stable, they remained identical. Their luminosity fluctuated in sync, rising and falling with a rhythm that was unmistakably coupled. One oscillated, the other matched it. One dimmed, the other dimmed with it. One brightened, the other brightened at the same rate. Opposite direction, same behavior, same timing. Even the microscopic dust distribution within each jet showed similar particle sizes, as if whatever initiated the outflow affected both channels equally. By the end of the fourth day, NASA, ESA, JAXA, and CNSA analysts were all circling the same reluctant conclusion: whatever was happening wasn't random, it wasn't chaotic, it wasn't typical outgassing in any form known. 3i Atlas had produced a matched pair of symmetric, collimated, rotation invariant jets. The first interstellar object ever observed, creating something like dual-directed exhaust. The working term that started appearing in emails, carefully worded, buried deep in attachments, was dynamic bipolar venting. But everyone knew what they were really thinking. If nature produced this, it did so through mechanisms we don't yet understand. If it didn't, then 3i Atlas was doing something unprecedented. And the world was about to realize that the twin jets weren't just a feature. They were a warning that the object hadn't finished surprising us, not even close. By the time the twin jets were confirmed, the scientific community had already reached a strange, uncomfortable threshold. They were no longer simply observing 3i Atlas, they were reacting to it. Instruments were being reoriented, schedules rewritten, missions reprioritized. And at the top of that list was NASA's Parker Solar Probe, which, by extraordinary coincidence, had been on an orbit bringing it close to the comet's interaction region shortly after perihelion. Parker was never designed to study interstellar objects. Its purpose is to graze the sun's outer atmosphere, to dive repeatedly into brutal streams of charged particles and magnetic turbulence. But its magnetometers, plasma analyzers, and high-cadence field detectors make it uniquely capable of reading the invisible fingerprint of anything disturbing the solar wind. And 3i Atlas was disturbing it in a way no one foresaw. On its approach to within a few million kilometers of the comet's extended interaction boundary, Parker encountered something the mission scientists would later describe as a localized magnetic twist, a coherent, rotating magnetic structure embedded in the solar wind, lasting far longer than any transient event should. In the raw data, it appeared as a helical spike, a sudden tightening of the magnetic field lines. The sun's Parker spiral, the predictable rotating pattern of solar magnetism, briefly kinked as though twisted by an external hand. These distortions usually snap back in seconds. This one persisted. Parker flew through its outer edge, and for 7 full minutes, the spacecraft recorded a stable, swirling magnetic pattern, coherent, directional, organized, a structure. That word ricocheted through every analysis channel the moment the data was decrypted. A magnetic field can surge, it can ripple, it can break, but it does not assemble itself into a stable shape unless something is sustaining it. And the direction of that twist pointed back unambiguously toward 3i Atlas. Immediately, the questions began. Could cometary outgassing create magnetic structures? Not in any known sense. Comets do produce induced magnetospheres when solar wind interacts with their outflow, but those fields are weak, uneven, and entangled with chaos. They don't twist into helices. They don't maintain coherence. They don't persist long enough for a spacecraft to fly through them like Parker did. Something about this object, this interstellar fragment, this shape-shifting, jet-emitting enigma was generating or manipulating magnetic fields more strongly than anything its size should be capable of. The hunt for natural explanations began immediately. The first theory to gain traction was the ferromagnetic grains model. It proposed that the nucleus contained pockets of iron-rich material inherited from its ancient parent system, perhaps remnants of a supernova ejector cloud. If the object was spinning, iron grains could align temporarily, creating transient magnetic patches. But even the most optimistic simulations showed these alignments collapsing within milliseconds, torn apart by rotation and outgassing. They could not create 7 minutes of coherence. They could not reshape solar wind fields. A second theory emerged: ancient stellar ejecta. Some researchers speculated 3I Atlas might have originated in a region rich in exotic isotopes or magnetically active crystalline silicates, materials forged in the violent final moments of dying stars. If the nucleus contained a dense, rigid core of such material, it could perhaps leave a magnetic imprint on its immediate environment. But again, the idea faltered. Even neutron star-born crystals wouldn't behave this way unless the object possessed a strong internal magnetic moment, and nothing about its prior observations hinted at one. Then came the third theory stranger, more controversial, but increasingly difficult to dismiss: paramagnetic carbon structures. Carbon, when exposed to interstellar cosmic rays and deep space irradiation, can undergo transformations. It can become amorphous, crystalline, graphitized, or even enter exotic states resembling nanostructured lattices. Some of these states, in theory, could exhibit weak paramagnetism, enough to distort local fields if arranged in large, ordered networks. But for that to happen, 3I Atlas would need an internal framework of carbon unlike anything seen in any interstellar object. Not dust, not soot, a structure, a lattice, a skeleton. And if that were true, it meant something even more unsettling. The unusual shape changes, the rotation stabilization, the twin jets, all could be manifestations of deeper internal organization. Not intentional, not designed, just an emergent property of a material structure far more complex than ice and rock. But if any one of those explanations was correct, Parker should have seen something else: thermal spikes, particle flux surges, magnetic harmonics. It didn't. It saw the twist and then silence. The more the data was scrutinized, the stranger it became. The magnetic twist was too clean, too symmetrical, too contained. It behaved almost like a plasmoid, a magnetic bubble with defined boundaries, yet it wasn't drifting away from the source, it was anchored to it. Parker's trajectory only skimmed the outer shell of the anomaly, but models showed that if it had passed nearer the center, the readings would have been far stronger, which raised an uncomfortable question. What would have happened if Parker got too close? No one was willing to ask that publicly. Internally, it was all anyone could think about. The twist wasn't merely a field anomaly. It was a message, though not a deliberate one. A message written in physics. This object had structure, magnetically responsive structure. Something inside 3I Atlas was interacting with the solar wind in a way that preserved coherence. A frozen lump of interstellar debris shouldn't do that. The debate widened. Some argued the magnetic twist was an imprint of the perihelion explosion, a leftover vortex of charged particles. Others said it was a toroidal bubble produced by the twin jets. One group proposed a radical idea: that the object's internal reorganization during the lull had lined up conductive pathways, creating a temporary magnetic dipole. But if that were true, the dipole should have been visible in earlier data. it wasn't. As new models poured in, the unspoken truth became harder to avoid. Whatever was inside this object, whatever survived billions of years in interstellar space, whatever restructured itself during the perihelion reset, had properties the solar system wasn't prepared for. The magnetic twist was a fingerprint of that hidden core. It wasn't a sign of artificiality. It wasn't evidence of intent, but it was unmistakably anomalous. A magnetic structure with coherence, a stability that defied spin and chaos. A tight, anchored twist in a region where such order should be impossible. Something inside 3i Atlas was synchronized. And if the Parker data was right, the magnetic twist wasn't weakening as the comet receded from the sun, it was growing. For weeks, 3i Atlas has been described as strange, volatile, unpredictable. But the newest data offers something different. A story. Not a metaphorical one, but a literal physical record etched into the object's surface, like the rings of a tree or the growth lines of a shell. Except these layers aren't chronological, they're directional. They're scars of motion. Signs of a long voyage through environments our own solar system could never produce. What first drew attention was the texture. High-gain radar from the Goldstone network, combined with solar grazing reflectance maps from SOHO, revealed a series of ultra-thin, alternating microlayers on the sunward hemisphere of Atlas. At first, these were classified as typical cosmic ray baked crust, the kind you expect from an interstellar object bombarded for millions of years. But the pattern wasn't random. It repeated, and not in depth, but in angle. Each layer was offset from the one below it by a shallow, consistent tilt, almost like shingles overlap by a steady, directional wind. Except this wind wasn't any force known in our system. Scientists started comparing the micro layers to those on certain meteoroids that pass extremely close to the sun objects, that skim the corona, survive, and come back with ablation patterns that tell you exactly how the solar plasma flowed across them. Only Atlas hadn't done that here. It had done it somewhere else, multiple times. When researchers ran thermal reflective inversion models, they found something astonishing. At least 4 distinct sets of layer geometries, each consistent with a different stellar flux regime. One set suggested long-term exposure to a red dwarf's weak, erratic ultraviolet output. Another hinted at a blistering encounter with a much hotter star, something with a harsh, dominant blue spectrum that scorched inorganic minerals into thin, high-contrast films. A third set showed abrupt erosion patterns typical of intense stellar flares. But the one that drew the most attention was the fourth, a smooth, almost delicate micro layer with grain alignment that only makes sense near a main sequence star with a solar-like wind. Except the orientation was wrong. The heating profile didn't match a flyby at high speed. It matched something slower, something more deliberate, an orbital capture followed by escape. No one wanted to say it, so they didn't. They only logged the data. The layers themselves weren't static. ESA's Vigil mission detected a phenomenon that researchers are calling microlayer, peeling thin sheets, curling and separating from the nucleus like blistered paint. Not random sublimation, not thermal fatigue, something rhythmic. The peeling repeats every few kilometers along the surface, as if Atlas had heated and cooled under tightly cycling conditions for ages, conditions you'd expect near a variable star that brightens and dims on short timescales. Put simply, Atlas wasn't forged in one environment. It was patterned by many. But the real shock came when they simulated the cumulative radiation exposure. If all the layers were the result of cosmic aging alone, Atlas should be half vaporized by now. Instead, the layers show selective stripping, almost like the outer shell kept resetting, shedding, reshaping as it passed through each new stellar system. This wasn't a quiet journey. This was a body battered, reformed, and battered again. The more scientists examined the microlayer structure, the harder it became to classify Atlas as a typical interstellar comet. It didn't drift for billions of years in a single cold void like a fossil in deep time. It moved, and whatever path it took forced it through environments wildly incompatible with its survival. That's why the microlayers were thin. That's why they peeled. That's why each represented a distinct episode, a distinct furnace, a distinct passage. Atlas had been somewhere hot, somewhere chaotic, somewhere with flares that could tear an object apart, yet it endured. Maybe it wandered into young, violent systems still filled with debris. Maybe it skimmed accretion streams around forming stars. Maybe it was tossed between gravitational interactions we don't yet understand. What's clear is this: Atlas is not an untouched relic. It is a survivor, a veteran of multiple stellar neighborhoods, a traveler with a skin full of history. Look closely at the combined layering and you see something that feels almost intentional. Each micro shell shaped the next. Each incredible encounter hardened or weakened a different part of the nucleus. Over time, Atlas became asymmetrical, not by accident, but by accumulation. Its current, unstable, ever-changing geometry, the elongation, twisting, and compression seen after perihelion, suddenly makes sense. This object wasn't built to be stable. It was overwritten by thousands of forces, thousands of times. What Parker Solar Probe and Vigil observed wasn't a comet falling apart. It was the latest entry in a geological autobiography billions of years long. If each microlayer marks a stellar encounter, then the peeling now occurring near the Sun suggests this: Atlas is shedding its history, not violently, not chaotically, but with a kind of slow, exhausted inevitability, like a traveller arriving at its final destination and finally laying down the weight of its journey. Researchers don't know whether Atlas will survive another decade. But one thing is now certain: whatever it is, wherever it came from, it has been shaped by far more of the galaxy than we ever imagined. The moment 3I Atlas tore itself open at perihelion, when that impossible geometry-shifting eruption lit the corona, every major observatory on Earth was pointed at the blast. Everyone expected chaos in the data: noise, scattering, shock fronts, ionized debris. And that's exactly what the professional arrays saw. But not everyone looking at Atlas was a professional. Across the world, dozens of amateur radio astronomers, people with backyard dishes, repurposed satellite receivers, and software-defined radios, reported something else entirely: a narrowband spike, not a transmission, not a pattern, just a single razor-thin surge in a frequency range where nothing should be happening. It lasted less than half a second. It appeared in 3 continents worth of logs, and it occurred at the exact timestamp of the perihelion detonation. Professional arrays dismissed the amateur claims at first, until 2 small but credible university labs confirmed they'd seen it too. The spike was faint, buried in system noise, but unmistakably present. A sudden coherence in the spectrum between 2 normally chaotic thermal bands. If it were communication, it would have structure, pulses, variation, modulation. If it were random, it wouldn't appear simultaneously across stations thousands of kilometers apart. It was neither. Researchers quickly ruled out the obvious candidates. Solar plasma oscillations? Wrong frequency. Instrumentation glitch? Impossible across unrelated hardware. Lightning, ionospheric reflections, terrestrial interference, none match the time correlation or spectral footprint. Cometary radio emission? Comets don't produce sharp line spikes at all. After a week of reanalysis, the consensus wasn't certainty but concession. Whatever caused it did not fit any known emission mechanism. The spike wasn't strong. What made it alarming was its purity. Natural broadband noise spreads and smears. Even synchrotron bursts, the most coherent astrophysical events we know, still have width. Atlas's spike was so narrow that one engineer compared it to a piano string vibrating when no one touched it, a single frequency ringing out briefly, cleanly, with no precursor and no decay. One of the lead analysts described it this way: if this were a signal, it would be intentional. But it can't be a signal, so that leaves us with something stranger, a physical process we do not yet have the math for. The leading natural hypothesis is something called compressive plasma resonance, a speculative effect where rapidly collapsing material could momentarily trap and focus electromagnetic energy. The problem? No one has ever observed it. No model predicts it. Most textbooks insist it can't happen. Yet Atlas seems to have done something that required an explosive restructuring of the nucleus, briefly forced charged particles into a coherent configuration, and released energy at one sharply defined frequency. That kind of coherence takes order. Not intelligence, just physics behaving in a way we haven't seen before. The spike didn't tell us anything. It didn't transmit data. It didn't encode meaning. But it did tell us change happened. Deep internal change. Some rapid transition within Atlas's core, some pressure collapse or crystallization wave or magnetic realignment generated a momentary lockstep vibration in the surrounding plasma. Those who study the event now think of it not as a message, but as a signature, a byproduct, a consequence of an unknown internal mechanism crossing a threshold we don't understand, a moment where the rules did something unexpected. Weeks later, as data was cleaned, filtered, and compared, analysts found one more detail that shouldn't exist. The narrowband spike was followed about 140 milliseconds later by a faint, ultra-low frequency dip in the opposite direction. Not a signal, not information, just a response, a ring and a counter-ring, an impulse and a recoil, as if Atlas briefly resonated and then damped itself out. No one has a model for that. No one is pretending to, but for the first time in this investigation, scientists are saying the quiet part out loud. Whatever is happening inside Atlas is not just chemistry or sunlight or gravity. It is something new, not artificial, not intentional. Just a physical process we do not yet have the math for. One that waited until the moment of closest approach to our star to reveal itself. Perihelion is over. The sun has done its work, and 3i Atlas is already retreating along its outbound trajectory. To the casual observer, it might seem like the drama is fading, that the object is cooling down and drifting silently into the outer solar system. But the scientists who have spent the last weeks watching every pulse, every jet, every spectral anomaly know that this is only the beginning. Perihelion didn't end Atlas's story, it transformed it. And now the real question is, what comes next? For the first time, simulations based on the post-perihelion telemetry and shape models are converging on a disturbing picture. Atlas is no longer a single, intact nucleus. The data suggests that the outer layers, the micro-shelled, peeled, scarred surfaces described in previous chapters, have entered a phase of mechanical instability. Unlike typical comets, which fragment into irregular clumps when torques and outgassing forces become too strong, Atlas appears poised to tear itself into thin, elongated sheets. These sheets are not randomly oriented. The modelling shows that existing rotation axes, combined with residual stress from the perihelion reset, create shear planes along which the crust will likely delaminate. The internal mass distribution, which had stabilized in the immediate aftermath of perihelion, is now misaligned with the angular momentum vector. That misalignment creates torsional stress, and the simulations show that rather than splintering violently, Atlas will likely produce successive layers that peel and twist, almost like a deck of cards, slowly fanning apart. This is not an abstract prediction. Observational evidence is already lining up with it. Images from SOHO, Vigil, and several ground-based adaptive optics arrays reveal tiny arcs beginning to separate from the main nucleus. These aren't dust jets or sublimating ice clouds. They are coherent fragments of the outer shell, thin enough to catch solar glare but substantial enough to persist for hours. Analysts are now using these early signs to refine models of how each sheet might behave once fully detached. The conclusion is startling. If the current rotation and torque conditions remain unchanged, the flaking will expose previously hidden interior layers, creating a natural cross-section of the comet's internal structure. Unlike typical comets, which only give glimpses of pristine material when large chunks break off unpredictably, Atlas is on track to slowly reveal its inner composition over a period of weeks. This unfolding process presents a rare observational opportunity. For the first time, the combined micro-layer peeling, the twin jets, and the rotation-stabilized nucleus align to create what researchers are calling a visibility window. This is a brief period in which the sun will illuminate Atlas at the right angle for Earth-based telescopes to capture high-resolution imagery of the freshly exposed layers. It is, in effect, a natural CT scan of an interstellar object. Astronomers will be able to directly observe stratigraphy that is billions of years old, built in multiple stellar environments, and altered by cosmic rays, collisions, and perihelion stress. The models predict that these exposures will occur in staggered stages, lasting anywhere from hours to several days for each segment of the crust. This means that observers on Earth, with precise timing and instrumentation, will have a fleeting but unprecedented chance to examine an object that has travelled between stars and survived multiple violent environments. The stakes are high. Unlike ordinary comets, Atlas's sheets are thin, fragile, and likely to be carried away by the solar wind as soon as they lose structural integrity. Missing this window could mean that the internal layers collapse into indistinguishable dust before detailed study is possible. Observatory teams around the world are currently scrambling to coordinate their efforts. For once, professional and amateur astronomers alike are sharing data pipelines in real time, aware that timing is everything. Every exposure, every spectral scan, every polarization measurement matters. What makes Atlas's post-perihelion behavior especially extraordinary is the apparent regularity of the flaking. While traditional models of comet fragmentation rely on chaotic surface failures or sudden gas pressure bursts, Atlas's sheets are predicted to peel in a near-predictable rhythm, guided by the interplay of its shape, dynamics, rotational momentum, and residual stresses from perihelion. In some ways, it is like watching a machine in slow motion. Each layer peels away, twists briefly in the solar radiation, and reveals another layer underneath, only to begin the process again. This rhythmic peeling is accompanied by subtle spectral shifts. Early readings suggest that each newly exposed layer has a slightly different signature in reflected light and near-infrared spectra, indicating compositional variations. The implication is profound. Atlas may not be a homogeneous body at all. Each layer could correspond to different phases of formation in separate stellar systems, each carrying its own history of radiation exposure, chemical processing, and collisional events. Already, the modelling teams are working to forecast the timing of the most significant layer exposures. According to current projections, Earth will have the best view over the next 2 to 3 weeks when the nucleus orientation, solar illumination, and orbital trajectory converge to produce optimal contrast. After that, the sheets may twist out of alignment, scattering light in ways that obscure fine detail. Observatories in the southern hemisphere have been given priority due to Atlas's path along the ecliptic plane. Instruments ranging from adaptive optics-equipped telescopes to polarimetric imagers are being readied for the first full-resolution capture of each delaminated surface. The implications of these observations extend beyond mere curiosity. Atlas's outer layers may hold clues about interstellar chemistry, the physics of long-term cosmic ray exposure, and the evolution of materials under repeated stellar encounters. Observing the peeling sheets in real time could also reveal mechanical processes never before documented. Stress propagation through irregular ice-rock mixtures, torsional responses of non-gravitational torques, and the potential for anisotropic outgassing in objects with complex internal stratigraphy. Every sheet that flakes off is a natural experiment, a laboratory for physics that cannot be recreated on Earth. Yet the process is not without risk. The simulations indicate that once the flaking begins in earnest, Atlas may undergo sudden shifts in rotation or axis alignment. The peeling sheets themselves could generate reaction forces strong enough to alter the nucleus's trajectory slightly, introducing unpredictability in later exposures. This means that the very process allowing astronomers to observe the interior could also obscure parts of it if the object tilts or rotates faster than expected. Researchers have described the situation as balancing on a knife edge. Atlas's next few weeks will determine whether the observation window is a treasure trove of data or a missed opportunity. Despite these uncertainties, the scientific community is preparing for a historic observation campaign. International collaborations are coordinating scheduling across multiple observatories, ensuring that polarimetric, spectral, and high-resolution imaging data can be collected simultaneously. Amateur networks are being incorporated into the effort, with participants trained to time their observations to complement professional instruments. Even the orbit of Atlas is being tracked with unprecedented precision, so that predictions of flake detachment and visibility can be updated in near real time. The broader significance of Atlas's post-perihelion behavior is already becoming clear. For the first time, humanity has a chance to peer inside an interstellar object, not through models or approximations, but directly. Each layer peeling away carries with it a story of formation, survival, and exposure to the galaxy's harshest conditions. What Atlas reveals about itself now could reshape understanding of planetary system formation, interstellar chemistry, and the life cycles of bodies traveling between stars. In the coming weeks, as the sheets continue to delaminate, every flash of sunlight off the nucleus, every newly exposed surface, every spectral anomaly will be watched closely. Atlas is, in a very real sense, revealing its autobiography layer by layer, exposing the journey as travelled over billions of years. And as Earth-based observers prepare to capture this unfolding, one thought hangs over the scientific community. What we see now may only hint at the interior's deeper secrets. Perihelion was a climax, but the story is far from over. The galaxy has written its history into Atlas, and now, for the first time, we have a window to read it. The past 44 days have been unlike any period in modern astronomy. From the sudden outburst at perihelion to the twin jets defying rotation, the magnetic twist Parker Solar Probe recorded, the micro-layer peeling, and the ephemeral narrowband spike, 3i Atlas has challenged every assumption we once held about small bodies, interstellar debris, and the quiet, predictable mechanics of comets. But the story isn't just about data points, light curves, or trajectories. It's about perspective, what it means to witness, in real time, an object that has traversed the galaxy, survived countless stellar environments, and now reveals itself on our doorstep. The first implication is scientific. and it is immediate. Atlas has forced a reconsideration of the cohesion and mechanical behavior of interstellar ice. Models built from decades of solar system comet studies assumed relatively simple physics: outgassing, fragmentation along predictable axes, thermal stress limited to solar heating. Atlas defied all of that. Its outer crust peeled in sheets rather than clumps, rotated unpredictably yet maintained certain stable orientations, and produced magnetic and spectral anomalies no ice-rock mixture should generate. The mechanics of interstellar ice, it seems, are far more complex than previously imagined. Its internal structure responds to cosmic rays, stellar encounters, and torques in ways that cannot be captured by Earth-centric models. The data we are collecting now will likely reshape textbooks, inspire new lab experiments simulating cosmic ray irradiation, and force theorists to develop a physics that can account for sheets peeling under torsion in zero-gravity conditions. The second implication is systemic. For decades, comet modelling has relied on a set of assumptions derived almost entirely from our solar system. We assumed that mass, spin, and outgassing behaviours could predict future evolution. Atlas has demonstrated that these assumptions are limited, possibly catastrophically so when applied to truly interstellar objects. Our models are now being rewritten to include the effects of multistellar irradiation histories, structural reorganization after perihelion equivalent events, and the surprising role of magnetic and plasma interactions in shaping cometary behavior. Each discovery during these 44 days has exposed the fragility of our understanding and the vastness of phenomena we have yet to encounter. The third implication is operational and aspirational. 3I Atlas has made the case for missions that no longer treat interstellar visitors as rare curiosities. Its appearance and the wealth of data collected demonstrate that objects from other star systems carry information. We can read information about stellar formation, chemical evolution, and even interstellar physics, but only if we position ourselves to study them. Future missions may no longer wait decades to intercept comets within the solar system. Instead, rapid response probes could be launched toward newly detected interstellar objects, equipped with spectrometers, radar, and even magnetic and particle field sensors to capture phenomena like the twin jets or magnetic twists. Atlas has turned the idea of reactive astronomy into proactive exploration, a chance to chase these cosmic travelers before they leave our reach. But the final and perhaps most profound implication is philosophical. Atlas is a messenger, though not a conscious one. It is matter sculpted by forces entirely alien to the solar system: the birth of distant stars, the death throes of massive suns, the cold emptiness between, irradiated by cosmic rays for billions of years. Every layer we now see peeling away carries a story not of our own system, but of others' histories written in ice and rock and magnetic fields, travelling across the galaxy to be witnessed by human eyes. In observing Atlas, we are, for the first time, seeing a tangible bridge between our world and countless others. The object has survived ejections, near collisions, close stellar passes, and the slow drift of interstellar time. And here it is, fleetingly illuminated by our sun, revealing its story to instruments built by humans, barely a century old. There is a sense of awe, yes, but also of humility. Our understanding of matter, physics, and history is incomplete, and we are encountering evidence that the galaxy itself is stranger than we have allowed ourselves to imagine. In these 44 days, we have also been forced to confront the limits of our perception. Instruments saturated, anomalies baffled even the most experienced observers, and theories crumbled under the weight of raw data. Yet the very difficulty of observation has brought collaboration to a new peak. Space agencies, amateur astronomers, theoretical physicists, and instruments engineers have shared data and insight in near real time. The experience has proven that the cosmos does not wait for preparation, but those who pay attention can bear witness to unprecedented phenomena. And so we zoom out. The 3I Atlas, now receding, remains a twisting, flaking, magnetically complex body in the outer solar system. To telescopes on Earth, it is a faint glow, a cometary ghost that defies categorization. Yet in those 44 days, it has changed everything. Our models of interstellar objects, our understanding of comet physics, and our imagination about the galaxy. It has reminded us that matter, shaped by other stars, other systems, and other conditions, can travel billions of years and still arrive intact, telling a story older than our civilization. In witnessing Atlas, we are not merely watching a comet. We are seeing the galaxy in motion, the scars of countless suns, and the echoes of cosmic processes far beyond our home. Its peeling layers, its twin jets, its magnetic twists, and its fleeting spectral anomalies are chapters in a story that began long before the sun existed. And while the observations of the next weeks and months will add more pages, the 44 days of perihelion and its immediate aftermath have already transformed our place in the cosmos. We now know that the universe can produce objects we cannot fully predict, cannot fully model, and cannot fully explain. Yet in that impossibility lies the wonder. We are the witnesses to matter that has lived in the interstellar void, survived multiple stellar systems, and reached our solar neighborhood to reveal, however briefly, the boundless creativity of the galaxy. These 44 days have changed everything because they forced us to confront a reality more complex than any comet in our textbooks, more intricate than any solar system formation model, and more ancient than any human history. 3I Atlas will continue on its journey, receding into interstellar space, but it leaves behind a new benchmark for curiosity, exploration, and humility. Humanity has not merely observed a comet, humanity has glimpsed the galaxy's memory, written in ice, rock, and magnetism, and it will not be forgotten.